Well, hello there to all my Math 103 students all over New York State and wherever else you're from. I hope your families are doing fine as we continue to get through this crazy period of time in our lives. And as we get closer to the end of this course, we are basically 2 classes away from you being hopefully ready to take this big final exam that I plan to give you for this course. So in thinking about that, I will be contacting you soon about material that I think you owe me that you have not gotten to me yet. Probably sometime over the next few days, I will be contacting you by email to let you know what that situation is. Also, we are going to continue to work on some more sheets to get you ready for the final exam. And then we're going to be pretty much there. And it's going to be your turn to show me what you know and what you can do with the material that we have learned in this course. So to start with today, we are going to now go over exam review number 2, virus exam review number 2. So I'm going to bring that in at this time, and we will share that, and we will take a look at that situation today, and we will get to work on it right away. So here we go. Well, the first question is not of surprise to you. You remember having seen it many times before. There are 370,000 people, none older than 105, living in the town of Tonawanda, which is the township just north of Buffalo. Explain or verify why at least 2 residents in the town must share the exact same birthday, month, day, and year. Well, this smells like a PHP maybe problem, right? And as a matter of fact, that's exactly what it is. Because of the pigeonhole principle, we can say we know at least 2 people, if not many, many more, have to share the same birth date in the town of Tonawanda, if the circumstances are what we're showing here. So let's take a look at that, all right? Well, if the oldest person is 105, how many potential birthdays are there for these people in the town of Tonawanda? Well, if we take 105 years old as the oldest a person can be, and we know there are 365 days in a year. Remember, the days go on top, years goes on the bottom so that they will cancel. All right? So how many possible birthdays does that give us for the people in the town of Tonawanda? Well, let's check it out. On my calculator, I do 365 times 105, which gives me 38,325 different days that people could be born on. And of course, we're assuming there are no leap years. So these are birth dates. Well, we have 370,000 people. Obviously, there are more people than available birth dates. So what has to happen? Duplication has to occur. So when you face this problem on the final exam, make sure you indicate to me why duplication does have to occur. And by showing me that there are 38,325 birth dates that are available for people who could be as old as 105 years old, and knowing that there are 370,000 people we're talking about, it is obvious that duplication will have to occur. Okay, let's go on. Question B. Jim is laying out a hockey rink in his backyard for his sons to play hockey in a rectangular shape to have dimensions of 120 by 50 feet. If he measures the distance diagonally across the rink, what length should it be to guarantee that this rink, is not a parallelogram, but is rather a rectangle? Well, to be a rectangle, the corner angles have to be 90s, right? So if we take this rectangle and we draw across this rectangle a line segment from one corner to the other diagonally, like so, what have we formed? We have actually formed two right triangles, right? And one of these right triangles, in fact, both of these right triangles, they have to be congruent, right? If this is a perfect rectangle. And if this is 50 feet, the width, and this is 120 feet, the length, what rule has to apply to the diagonal going across that rectangle? Well, I think you are all aware it's got to be the rule of Pythagoras, right? Which is c squared equals a squared plus b squared. And since I'm looking for the length of the diagonal, I am going to put the c squared on the left and the a squared plus b squared on the right. I'm going to call the diagonal x. So if I square x, it should be equal to the altitude here, or a. All right, I wrote 15 down there. I don't want that. I want 50, right? So let's change that. So it'll be 50 squared plus the base of the rectangle, which is 120 squared. So continuing the process, I square 50, I will get 2,500. If I square 120, I will get 144,000. Okay? And if I combine these two, I believe I will get 169,000. So you know that to obtain x, I simply have to find the square root of 169,000. So to determine the square root of 169,000, you do second and then x squared, of course. So on your calculator, second, x squared means it will give you the square root, right? So we want to do the square root of 169,000. So 169,000 square root. I get exactly 130. So the distance across is going to have to be 130 feet. And if it is 130 feet, then we know in the corners of this supposed rectangle, the angles are definitely 90 degrees. So this proves it. Okay, let's move on. The bag shown here to the right contains 4 red marbles, 3 white ones, and 1, 2, 3, 4, 5 blue ones. Okay? If you do not replace any marble in any draw, what is the probability of drawing or picking out at least 1 blue marble in 3 draws? Hint, first find the probability of never picking out a blue marble. Well, as you know, if we were to pick out at least 1 blue marble, it could be in the configuration blue, white, red. It could be red, white, blue. It could be blue, white, blue. There's 2 blue ones there. There's a ton of different outcomes that could happen there, right? And you know that in this bag of marbles, if we do not replace, this is just one configuration that's possible, or 3 configurations that are possible here. And we're doing this without replacement. So each time the number of marbles in the bag goes down. So the simplest way to accomplish finding this answer is to do this. Determine the probability of never picking a blue marble. Once you have that, you can find the opposite of that, which would be picking out at least 1 blue marble. So let's do that, all right? So how many marbles are there in the bag? Well, it appears that according to what it says up here, 5 and 3 are 8, and 4 are 12 marbles in the bag, right? So if we have 12 marbles in the bag, in the first draw, what's the probability of never picking out a blue marble in that first draw? Well, if there are 12 marbles, and if we're looking at the blue ones, there are 5 blue ones, so therefore there are 7 that aren't blue. So there are 7 ways out of 12 not to pick a blue marble in the first draw. Now we're not putting the marble we drew out back, so in the second draw, we don't have 7 marbles anymore that are not blue. We only have what? We only have 6 of them. So that would be 6 ways out of a total of how many left in the bag? Only 11. All right? And if we go to the third draw, we have only 5 marbles left in the bag that are not blue out of what? 10. So what is the answer to this? To find this probability, I simply multiply these numbers together. 30 on top times 7 appears to me to be 210. All right? And 10 times 11 on the bottom is 110. So I'm going to take 110 times 12. And when I do, I get 1,320 total outcomes that could occur. There are only 210 ways that I would not get a blue marble. So what is the probability then that I could pick at least one blue marble out of the bag? It's the opposite of what I've shown here. So it is 1 minus 210 out of 1,320. And if I change the 1 here to a 1,320 over 1,320 and subtract from it 210 over 1,320. By the way, I'm not worrying about reducing any of these answers. So if I take 1,320 minus 210, I get 1,110 ways out of 1,320 to get at least one blue marble from this bag. Okay, so remember, the hint is the key to this problem. You first want to get the opposite. Once you've obtained the opposite, you subtract it from 1, and then you are able to determine what it is you're looking for. Okay, let's go on. State by counterexample all quadrilaterals, can't read it here because I've got it blocked with my picture. All quadrilaterals or 4-sided polygons have right angles at each vertex. Now folks, you are aware of the fact that a quadrilateral is a 4-sided polygon. Are all 4-sided polygons filled with 4 right angles? To show that this is a false statement, all you have to do is what? Come up with one counter example. What would be the counter example or a counter example that would kill off this law? Well, are parallelograms all filled with right angles? No, they are not. All right? So that would be a perfect example of a quadrilateral that doesn't have all right angles. How about a trapezoid? Okay, so let me sketch a parallelogram here. A parallelogram would not have it. A trapezoid would not have that situation. Very poor illustrations, but you get the idea. Therefore, you just need to pick a counterexample. Don't forget that term when you come to take the final exam. Okay, look at statement E. If a multi-stage probability experiment, there are 5 outcomes in the first event, 11 outcomes in the second event, and 9 outcomes in the third event, how many outcomes are there in the entire combination experiment? The first event followed by the second, followed by the third. What do you do with these number of outcomes? Do you add them? Or do you multiply them? Well, the answer is you multiply them, right? So it is simply 5 times 11 times 9, or 55 times 9, and 55 times 9 will give you 495 possible outcomes. This is the BCP, right? The basic counting principle of probability. Okay, F. Describe how rational decimals behave compared to irrational decimals. All right, how do we do that? Well, what do rational decimals behave like? Well, they all come from what? Rational decimals. They all come from fractions that are divided, top by bottom. When you divide a fraction out, do you remember what happens when you divide them? They will either terminate or repeat. So you can write they R or T, right? What do irrational decimals do? Well, they don't terminate. They go on forever, and they do not show repetition. They can show a growing pattern, all right? But as we will review a little later in this sheet, okay, but they can be all over the place also. And you can use that arrow notation I talked about. So what do you want to say here? You want to say irrational decimals go on forever. They may show a growing pattern to infinity, but they never show repetition. But they definitely go on forever. Okay? So there you have it. Okay, look at G. In a combination probability experiment, if a first event has a probability of 4 out of 13 of occurring, and is followed by a second event with a probability of 5/9 of occurring, 5/9 of occurring, then the two events combined have a probability of what? All you have to do is multiply the individual probabilities together. The answer to this is obviously 20, and I don't know what 13 times 9 is off the top of my head, so I will multiply that out. 117. So the probability of the first event followed by the second event is 20 out of 117. You multiply the probabilities together. Informally prove that these 3 line segments below are indeed golden sections. We're going to actually hit on this idea a couple times today. But if you recall, for these to be golden sections, there are 3 properties that need to be satisfied. One is that YZ here divided by the length WX has to give us phi, the golden ratio. Also, the longest segment, AB, divided by the middle length segment, YZ, has to also give us phi. All right? And the third thing that has to be satisfied here is that if you take the length of WX, add to it the length of YZ, you should get the length of AB. Now, if you add 67.65 to 109.46, you will definitely obtain 177.11. And if you take, for example, the first one, 109.46, and divide it by 67.65, you will get 1.618034. 1.618034 rounded to 6 decimal places. And the same thing will happen here. 177.11 divided by 109.46 will also give us 1.618034, the golden ratio. So that's all you have to do, is show that those three things are satisfied, and you have proved that these indeed are golden sections. Okay, let's go on. How many folds of a large piece of paper are required to reach a thickness of 1,448,576 sheets of copy paper? Well, if you remember, if you fold a piece of paper in half, you are doubling its thickness. If you fold it again, you are doubling its thickness layers. If you fold it again, you have doubled its thickness layers. Each time you are doing a power of 2. So what power of 2 do I need? 2 to what power is going to be equal to 1,048,576. Okay? Well, this is a trial and error problem. T and A, baby. You got to trial and error it. So let's try maybe 2 to the 15th power. Well, 2 to the 15th is only 32,768. We're just a little short. So let's try 2 to the 17th and see if that works. 2 caret 17 equals 131,072. Not quite yet. All right, let's keep going. Let's try maybe 2 to the 20th. 2 to the 20th power. Ooh, right on. 2 to the 20th power gives me 1,048,576 sheets of thickness. So if you are faced with this problem on the final, you want to make sure you do it by trial and error to determine the answer to this question. All right, let's have a look at question J. Know the ratio of two consecutive Fibonacci numbers, the larger divided by the smaller, should result in an answer very close to phi, the golden ratio. Show one such calculation, f sub n plus 1 divided by the one prior to it, f sub n, indeed gives you that result. So all you need to do is pick a value where n is greater than 14. Well, how about if we try the 20th Fibonacci number, 6765. I'll let that be f sub n plus 1. I'll divide it by f sub n, which will be the one prior to it, 4181. And all I need to do is to show that this gives me the golden ratio. So I take a calculator, 6765. I divide it by 4181. And when I do, I get 1.61803339. Rounding this off, it'll be what we use for the golden ratio, 1.618034. Pretty simple question, right? Don't want to miss that on the final, do you? You know what? These sheets are designed to show you exactly what I'm going to ask you on the final exam. So these exam review sheets, plus the extras we're going to do, are the sheets you want to study to make sure you know what you're doing when you come in and take the final exam. So please be certain to spend time studying this material. Let's go on. Given the numbers 4181 and 6765, then the next two larger Fibonacci's in the series must be what numbers? Well, if you go up here and cheat, you can see I didn't give you the opportunity to be able to cheat with the table of values up above, but all you have to remember to do is the two previous Fibonacci numbers add together to give you the next one, right? So I need to take 4181, add to it 6765, and come up with that answer. So if I take 4181 and add to it 6765, I obtain the next Fibonacci number, 10,946. Well, if I want the next Fibonacci number after that, I simply take what? 10,946. I take the number that was previous to that, 6765, and I add those two together, and 6765 added to that number is 17,711. So the Fibonacci number I was looking for, the next two larger numbers, were 10,946 and 17,711. Okay, let's take a look at question L. Write 655 as the sum of non-consecutive, non-adjacent Fibonacci numbers. Okay, now if you recall, you're going to have to remember how to do this on the final. You want to find the closest Fibonacci number to 655 that is larger than it. And of course, as you can see from this list, that would be 987. So if I take 987, all right, that is equal to what number? I'm sorry. Let me start this again. I obviously messed up, okay? Let me erase that, and I hope you realize I made a very bad error there. Let's go back and start over. Write 665 as a sum of a non-consecutive Fibonacci's, not 987. It's already a Fibonacci. All right, so I want to take 655, and I want to take the closest Fibonacci number to it that is smaller. So I'm going to take 655. The closest Fibonacci number that's smaller is 610. So how much did I miss 655 by? Looks like 45, right? Okay. If 45 is a Fibonacci number, I'm all set. I'm all finished, right? Well, it's not, so I got to keep going. What's the closest Fibonacci to 45 that is smaller than it? Well, let's see. That, I believe, would be 34, all right? And 34 increased by 11 gives us 45. Is 11 a Fibonacci number? No, it is not. So I must continue. 610 plus 34. The closest Fibonacci number to 11 that is smaller is 8. And how much did I miss 11 by? By 3. Now wait a minute. 3 is a Fibonacci number. So I am all finished with this problem. Okay? And if you notice, if I circle these numbers in this listing up here, 3, 8, 34, and 610, they are not next to each other in the showing of these numbers. So they are non-consecutive. They aren't adjacent to each other. So this is the correct answer we need to find. And of course, I will be asking for you to do one of these on the final exam. All right, let's continue. Okay. Given this UPC code for Friendly's Reese's Peanut Butter Cups, okay, let me move this out of the way. Peanut Butter Cup Sundaes, determining the missing value X in this code. Well, if you recall, you multiply these by 31, 31, 31, 31, 31. The sum of all these numbers that we obtain, written in mod 10, have to add up to 0 mod 10. So I simply multiply by 3, 1, 3, 1, 3, 1, 3, 1, 3, 1, 3, 1. When I do this, I get 0, 2, 27, which I will change just to 7 mod 10, 8, 3x, 9, 0, 0, 0, 2, 9, and 4. So now what I'm going to do is add these numbers together. Want to make sure you add them correctly. So 2 and 7 is 9, and 8 is 17, 26, 28, 37. I believe I got 41. I'm going to add it the other way just to be sure, since I'm doing it in my head. 9 and 4 is 13, 14, 15. Adding 9 more is 24, and 8 is 32. 32 and 7 is 39, and 39 plus 2 is 41. So it looks like I did all right. So now I have this sentence. 3x plus 41 has to come out equal to 0 mod 10. Now, what do I ask myself now? Well, what must 3 times x end in so that 41, when it's added to the result of 3 times x, it becomes a 0 on the end? Well, I think you can all see that 3 times 3 has to be what? 9, right? 41 increased by 9 would make it a 50, which is 0 mod 10. So in this case, x would have to be equal to 3 to solve this problem. So the missing number in this Reese's Peanut Butter Cup Sundae in its UPC code is a 3. Recall there will be no credit cards on the final exam, only a UPC code or a bank routing number, one or the other. And I will always give you the digits you need to multiply by to solve the problem. Okay, any question there? Hopefully not. All right, let's go on to the next question. Determine whether or not this is a true statement. Show your work that helps you decide your conclusion is correct. All right, if you recall on these, the simplest thing to do is take the left-hand side and work it out in normal arithmetic. And then let's change it to mod 8. Well, let's see. 4 squared is 16, right? 6 times 10 is 60. And we're going to subtract 17. If I add 16 and 60 together, I get 76. And if I take 76 and subtract from it 17, I obtain 59. So what number is this? Mod 8. Is it 2? Okay. Well, let's see. How do you convert this? All right. Well, you simply take your answer, 59, and divide it by what? Your mod number, which is 8. All right. If you do this on a calculator, you'll find this goes 7 with a decimal here left over. All right. If you do 7 times 8, you'll get 56. The remainder I got was 3. So 59 is equivalent to 3 mod 8, not 2 mod 8. So this statement is what? False. Okay? So you have shown that this number is incorrect as it was, this expression is incorrect as it was stated. That's all you need to do. QED, done enough. Give an example of each type of number requested between the given numbers. Okay, what I need to do is find a rational number between these two guys. 4.8625, 4.8628. If I take those two and add them together and divide them by 2, I get the following answer. 4.8, let's see, 4, I lost it here. 4.86265. All right. Now, is that number between them? Well, if I put a 0 here and I put a 0 here, that's 50, 65, 80. 65 is definitely between 50 and 80. All right. Is this number that I have just found rational? The number I just found terminates, doesn't it? So therefore, it is rational. Okay? Done. Problem finished. What if I had asked for the same two numbers for you to find a number between them that is irrational? Okay? Same thing. You would divide the two numbers, add them together, divide them by 2. You would get 4.86265. But is this irrational? No, it's not. Now remember, there are three ways that you can solve this problem to make everybody happy and get the right answer. One way is to cheat and put an arrow after it. What does that arrow mean? We have made it into a number that goes on forever and the numbers are all over the place. Okay? So that's one way. Another thing we could do is we could simply put a bunch of numbers on here. Put 3 dots after it, just so the numbers are kind of all over the place. And this is telling the reader that what? This continues on forever and the numbers are wandering all over the place. Therefore, it's an irrational number. So that's another way to do it. All right? But my favorite way that we've discussed in class to do this is to do what? Okay? Put a pattern on it. You don't have to use any of the numbers that are there. You can just start your own pattern. How about 1, whoop, would help if I switched over to writing with the pencil here. 1, 3, 1, 3, 3, 1 followed by 3 3s, 1 followed by 4 3s. I think I've established the pattern well enough, don't you? And if I put 3 dots here, I'm showing the reader of the answer to this problem that I have come up with an irrational number, which is growing with a pattern that would continue to infinity and never stop. Okay. Okay, I believe we have covered everything on the sheet called Virus Exam Review number 2. So in our next video, which you are about to watch, we are going to continue and do at least 3 more of the extra sheets, I believe starting with extra sheet number 4. So if you have not downloaded them already or printed them or whatever you're going to use to be able to watch this as we do it, please do that at this time, and we'll see you in the next video. Take care.